This is a 12-minute non-technical presentation designed to give sales a better understanding of how impedance affects voltage and what kinds of problems the Pacific Volt low voltage regulator can resolve. Voltage is a measure of how hard electrical power is being pushed. Impedance and resistance are both measures of how much the system resists the flow of power. Impedance is a more complicated measure of electrical resistance. However, for this discussion, you can think of the two terms as being interchangeable. In North America, every building is connected to the electrical grid through a distribution transformer. The medium voltage feeder line, which runs down your road, is typically 7,200 volts. Buildings operate at low voltage, which is limited to 600 volts or less. The transformer divides the medium voltage on its primary side down into something usable, like 120 volts on its secondary side, before it is supplied to the building. The LVR, or low voltage regulator, works on the low voltage or secondary side of the distribution transformer. The single-phase LVR50 is available now, and our older three-phase models will be upgraded to sub-cycle hardware and reintroduced in the future. In order to comply to the voltage delivery standards, the voltage on a medium voltage feeder should stay within plus or minus 5% of 7.2 kV. The medium voltage input to the transformer rises and falls, depending on how much power is consumed on the feeder. This is especially true near the end of the feeder. The secondary circuit is defined as the low voltage side of the distribution transformer and the wires connecting it to the building. Historically, the secondary circuit voltage has received little attention. It was assumed that if the medium voltage feeder was regulated properly, the secondary would also be okay. However, four major trends are now disrupting the status quo. The adoption of smart metering systems that report the actual real-time voltage at the building, in addition to rooftop solar, energy storage, and EV charging, are all disrupting business as usual for secondary circuits. In short, Grid 2.0 is coming, and many of these changes will be disrupting secondary circuits. Just like on the medium voltage feeder, the impedance of the transformer and the secondary circuit conductors cause the voltage to drop in proportion to the amount of power being consumed. The amount the voltage drops depends on the amount of power being consumed and the impedance of the secondary circuit. Additionally, the longer the secondary circuit is, the higher its impedance is, which causes the voltage to drop more. Because there are millions of secondary circuits in North America, there is a strong economic pressure to reduce their cost, meaning smaller transformers and conductors which have higher impedance. Traditionally, the system was designed so that the voltage on the medium voltage feeder was kept high enough to accommodate for the voltage drop on these secondaries. This strategy worked well until rooftop solar came along and complicated things. The same impedance or resistance that causes the voltage to drop when energy is consumed also prevents the solar inverter from pushing the energy back through the transformer onto the medium voltage feeder. As more of the building's energy is supplied by the solar, the voltage at the building will begin to rise. This is because the amount of power supplied from the grid is being reduced or offset by the solar energy. If the energy consumption of the building is equal to the energy the solar is generating, there is no voltage rise or fall. This is because there is no power flowing on the secondary. If excess solar power is produced, the voltage at the building will need to be higher than the voltage at the transformer in order to overcome the impedance and get the energy to flow backward onto the feeder. The voltage on the medium voltage side of the transformer will also rise slightly. With more and more solar on the feeder, the voltage on the medium voltage feeder also begins to rise. Unless the voltage on the medium voltage feeder can be reduced, the voltage at some of the buildings will begin to exceed the maximum limit and their PV inverters will shut off. This is typically more of an issue towards the end of a radial feeder at midday. If the medium voltage can't be reduced because it is needed to support a large load at the end of the feeder, inserting an LVR will lower the voltage at the building while also allowing the power to flow back onto the grid. Conversely, during higher than normal loading, such as during EV charging, the LVR can raise the voltage to maintain voltage compliance. Note that for a given power flow, the amount of voltage drop on the secondary does not change. The LVR just raises the voltage at its output in order to maintain compliance at the building. The goal of CVR and volt-var optimization projects is to lower the voltage in order to reduce peak demand charges and/or reduce energy consumption. An LVR can be selectively applied to maintain the optimal voltage for customers which would otherwise drop below the minimum during high load periods. This allows for more reduction of the feeder voltage and therefore greater energy savings for these programs. For a building that is a long way off the road, an LVR can be installed in lieu of a primary line extension and moving the transformer closer to the building in order to shorten the secondary conductor. Additionally, an LVR can often be installed at the transformer to serve more than one connected house. We have now established that because of impedance, the voltage changes as the load changes, which brings us to the topic of flicker. Flicker refers to light intensity changing because the voltage is changing rapidly. Flicker is ultimately caused by large and rapid changes in load current. Flicker can originate on either side of the transformer. It can be caused on the primary by a large industrial load, and since transformers are magnetically coupled, flicker on the primary is also transferred to the secondary voltage, where it can be mitigated by an LVR. The LVR compensates for the change in voltage 20 times every cycle, which is 72,000 times a minute. This subcycle response will effectively mitigate flicker on the low voltage circuit. Secondly, flicker can also be caused by a rapidly changing load on the secondary side, such as EV charging, a large on-demand hot water heater, or a welder. Note that in this case the flicker is not transferred back onto the primary because it is a relatively small load change. Installing an LVR, preferably close to the building, will mitigate the flicker complaint. If two houses are connected on the same transformer, a large, rapidly fluctuating load at house 1 can cause flicker complaints at house 2. Where you insert the LVR will affect the two houses differently. Keep in mind that the rapidly changing load at house 1 is causing a voltage drop in both the transformer as well as in the secondary conductor feeding house 1. So placing the LVR at the transformer will correct the voltage fluctuations in the transformer and house 2. However, it will not totally correct flicker at house 1 because of the uncorrected voltage drop in the conductors feeding the house, which is causing the problem. Putting an LVR at house number 1 will mitigate their flicker complaint. However, it does not change the rapid load fluctuations, which are still causing lesser voltage drops in the transformer that are being transferred directly to house number 2. The traditional fix would be to put them on separate transformers or one larger transformer to lower the impedance in an attempt to reduce the voltage fluctuations to an acceptable level. Keep in mind that an LVR does not change the actual impedance of the secondary. Only installing a larger transformer and conductors can change the circuit impedance. However, the LVR effectively reduces the impedance to nearly zero because of its bidirectional line drop compensation and subcycle regulation. This makes it a valuable tool which compensates for the voltage problems on existing secondary circuits as the new grid continues to evolve and puts new stresses on the existing infrastructure. Thank you for your time.